Now in this class, I'm going to show you how to calculate the potential energy of a continuous mass. That is, in my previous lecture, I considered a particle lying on a horizontal surface. Mass of the particle, I considered it as m. By taking this as the reference point, when this particle is lifted through a height h, with respect to this reference, considering this as a datum line, what is the potential energy I calculated? Gravitational potential energy. Gravitational potential energy is equal to, as the particle lies above the datum line at a height h, I wrote it as mgh. Now the question is, instead of considering a block like this, what if I consider a rod of length L? For example, if you consider this a rod of length L and mass m. Now what I'm doing is, I wanted to lift this rod up like this. This is the reference level. Now I lifted it up like this and I kept it like this. Okay, initially it was lying on the horizontal surface. Now what I did, I lifted it and I kept it like this. Now I wanted to calculate what is the potential energy of this configuration. For a particle mass, you simply considered h, a height at which the particle is located, that you considered it as the height of the particle. But here, what should I consider as height? Actually, I should do it by integration method. Instead of doing that, directly I am giving you one alternate way. For a continuous mass distribution, height you should consider is the height of the center of mass, because it is a rod of uniform length, uniform mass distribution. So its center of mass will exactly lie at the center. As this vertical dimension is negligibly small when in this horizontal dimension is concerned, okay, so its center of mass will be exactly at the center. So when you lifted it up like this, okay, so initially the center of mass was on the ground only. Now when it is lifted up, the center of mass is at a height L by 2, because of which gravitational potential energy of this rod in this configuration is given by mg into L by 2. What if I consider this horizontal dimension also? That is, this is observation number 1 and this is observation number 2. In my third observation, what I am doing is, instead of considering a rod, I am considering a block now. I am considering a block. This is the horizontal line reference on which, horizontal surface on which I am considering a block instead of a rod. So you know the difference between the rod and block. Block means its length is L and breadth is B and mass I am considering is M. In this case, what I am doing here is, I am lifting this rod up and I am putting it in vertical position. Now it is in horizontal position. So now I wanted to put it in vertical position like this. That is like this I wanted to put it. That means I am rotating it and I am putting in this configuration. Now what is the gravitational potential energy associated? Here this vertical dimension is negligible because it is mentioned breadth is B. So before lifting up, what is the height of the center of mass? Exactly half of the breadth, that is B by 2 is the height of the center of mass. So therefore initial potential energy Ui, gravitational potential energy, is how much? mg into B divided by 2. When it is tilted and kept it like this, then what is the height of the center of mass? So in this dimension, the what is length? L only. So center of mass will be exactly at a height of L by 2. The center of mass is at a height of L by 2 from this reference line. So what is the final potential energy of the configuration? UF is equal to mg into L by 2. So as I calculated initial potential energy and final potential energy, if you wanted to calculate what is the work done by the gravity, which is conservative force, work done by gravity is equal to negative of change in potential energy, that is equal to minus of, what is delta U? UF. UF is how much? mg into L by 2 minus, okay, UI is how much? mg into B by 2. That is equal to how much you're going to get? Minus mg divided by 2 into L minus B. This is how I calculated work done by gravity in the case of a continuous mass distribution. So up to here, everything is okay. Simply we considered center of mass and we calculated. And same thing I'm extending to the case number 4. In this fourth case, what I'm doing is, here there is a table. Okay, this is a table. Assume that this is a table on which I placed a chain of length L and mass M, and out of which some portion is hanging freely like this. Okay, so let me call 1 by nth of the chain is hanging. Length of the chain I am considering is L and mass of the chain I am considering is M. Now I wanted to put it on the table by pulling it to the left direction. Okay, what is the work done by gravity and work done by external agent? Both the things I wanted to calculate. So here, work done by external agent, magnitude of work done by external agent and magnitude of work done by gravity, both are going to be same because there are no other forces acting on the body. So because of which, to calculate what is the work done by external agent, first I will calculate what is the work done by gravity, because calculating work done by gravity is very easy. Because gravity is conservative force, simply I will calculate potential energy and I will calculate what is the change in potential energy, which I call it as the work done by gravitation. So for that purpose, I should calculate what is the initial potential energy of the configuration. You can do it in so many ways, but the best way and simplest way is consider this horizontal level of the table as the reference level. Now this is my reference level. By considering this as my reference level, I am calculating what is the initial potential energy of the configuration. UI is equal to, okay, what is the initial potential energy of the configuration? Because 1 by nth, that means L by nth of the chain is hanging. So from this table, the distance of center of mass from this reference level is going to be how much? L divided by 2n, the distance of center of mass with respect to reference. So when I pull this chain, when this complete chain comes onto the surface, the center of mass is lifted through how much distance? L by 2n. So initial potential energy I wanted to calculate. I don't know what is the mass of this hanging portion. For that purpose, I will define one parameter which you call it as lambda. What is that? Mass divided by length, m by n. So what is the mass corresponding to length L by n? Mass of this portion I am calculating, that I am calling it as m dash, is equal to, okay, lambda, mass per unit length into length of this hanging part, that is how much? L by n. This is the mass of this one. So simply I am calling m dash, later I will substitute lambda L divided by n over here. Therefore initial potential energy of the configuration with respect to this level as the reference is given by UI is equal to, as the point of center of mass is below the reference level, here the potential energy is negative, so minus m dash into g into s. What is this distance? L by 2n, because distance of center of mass from this reference level is L by 2n. So when the complete chain comes onto the surface, okay, what is the final potential energy? UF is equal to 0. Why? This I considered as the reference level. As the complete chain is pulled onto the table, all the links of this chain are on the table only, because of which final potential energy is 0. Okay, therefore change in the potential energy delta U is equal to, what I can write? UF minus UI. UF minus UI. That is equal to, what is UF? 0. Minus into minus plus m dash into g into L divided by 2n. That is equal to, that implies, because gravitational force is a conservative force, therefore work done by gravity is equal to negative of change in potential energy is equal to, what you can write? Minus m dash g into L divided by 2n. This you can write it as, what is m dash? Lambda L divided by, what is lambda? Mass by length into capital L, I am writing it as it is, divided by n also I am writing as it is, into G into L divided by 2n. So in this, LL gets cancelled, because of which you will be getting m G L divided by 2n square. Okay, here minus sign I forgot. Work done by gravity is minus mgl divided by 2n square. As from work energy theorem, what I can say? Work done by the applied force plus work done by gravity. Initial kinetic energy 0, final kinetic energy 0. Everything is 0, because of which work done by the applied force is equal to, what I can write? Minus Wg, that is nothing but mg L divided by 2n square. So work done by gravity is negative, work done by external agent is positive. This is how I calculated the work done by applied force and gravity by using change in potential energy. Okay, because here the forces involved are conservative force. And next example I'm going to consider is the case in which we cannot calculate so simply the location of center of mass of the here, because it is L by n length, so half of the length is L by 2n, like that we calculated the location of center of mass. Sometimes it may not be straight away a situation like in this case. For example, here I am considering a hemispherical ball like this. This is a hemispherical ball, okay, lying on a horizontal surface. Okay, from here, let me assume there is some support over here. From here, a chain is hanged like this. Let me call length of the chain I am taking as L, and its mass is m, and radius of the spherical ball I am taking as r. So this is like this. Now I wanted to calculate what is the gravitational potential energy of this configuration. This is fifth case. So here I don't know what is the location of center of mass. If I know directly, I can write like this, but I don't know. So because of which I want to do it like this. By integration method only we can calculate, because it is a continuous mass distribution. So to calculate this, what I'm doing is I will consider a small elemental strip. I will consider a small elemental strip at an angle theta. At an angle theta with respect to the vertical. And this element length I am taking it as dl, and mass I am considering is dm. Okay, this angle I am taking it as d theta. Okay, so first I will calculate what is the height of the center of mass. By taking this horizontal line as the reference line, I will calculate what is the height of this center of mass for this small element dl. So as the radius is r, if you complete a right angle like this, as this side is r, component of r in vertical direction is r cos theta. So therefore height of this elemental strip is given by h is equal to how much you will be getting? R cos theta. With respect to this reference line, therefore potential energy du of element is given by how much? M. M is how much? dm into g into h is how much? R cos theta. So this is how I calculated the potential energy of this element. So total potential energy, if you want to calculate, what you should do? Simply you should integrate it between the limits. And g and r are constant. I am pulling them outside the integration. gr into dm cos theta. Okay, what is dm? Define again lambda. What is lambda? Mass by length. dm divided by dl. Through this, what you can write? dm is equal to lambda dl. Okay, this I am substituting back in this expression. So potential energy is equal to g into r into summation over. In the place of dm, what I can write? Lambda. What is dl? dl is nothing but r d theta only. That only I am substituting here. Cos theta into, in the place of dm, because the length of the sector is r d theta. R into d theta. And the value of theta is changing from, when this coincides with this vertical axis, theta is 0, and when it comes to this end, that I am taking as some arbitrary angle phi. Okay, that is equal to G is constant, R is constant, lambda and R also constant because of R square lambda into integration over 0 to phi cos theta d theta. That is equal to G R square lambda into integration of cos theta is how much? Sin theta. Between the limits 0 to phi. That is equal to G R square lambda into sin phi we will be getting. Okay, actually what is lambda here? Lambda is mass by length. That only I am substituting here. G R square into what is lambda? M divided by L into what is sin phi? If you take this end point, okay, then this total angle is going to be phi. We are between this blue line and this pink line. This total angle is phi. So that you can write it as theta is equal to L by R. That means phi is equal to total angle phi is equal to length of the sector is nothing but length of this string only or chain L divided by radius is R. So in the place of phi you can substitute L by R. That only I am substituting sin of L by R. This is how I calculated gravitational potential energy in a situation where I can't write straight away the value of the location of center of mass. Now in this case number 6, one of the important situations that we encounter in our mechanics is the simple pendulum. That is, here there is a bob of mass m, okay, suspended by string of length L. Okay, now what I'm doing is I'm simply pulling this bob to the right direction through, let me call it as a small angle theta, through a small angle theta with respect to the vertical, and I kept it over here. Now, what is the gravitational potential energy of this configuration? And what is the work done by the gravity? All these things I wanted to calculate now. This is one of the important observations that we use all through oscillations also. Okay, so to calculate this, first we should fix our reference point. You can fix your reference point either at the center of mass of this bob or with respect to this suspension point. You can take the datum light at any point. So first I will calculate with respect to line number 1 and later I will calculate with respect to line number 2 also. First I am calculating by considering line number 1, the line passing through the center of this bob. Okay, so when bob is displaced through a small angle theta, the center of mass of this bob is lifted through a small height h. Am I right? It is lifted through a small height h. So gravitational potential energy Ug is equal to what I can write? Mass of the bob into g into h. Directly I can write. But h is not given, only L and theta are given. Then by using geometry, I should calculate what is the value of h. Okay, for that purpose, from center to this vertical line, drop a normal. Okay, then if this is L, this length also L only. Then component of L in this direction is given by how much? L cos theta. So the distance from this point to the suspension point is L, and distance from here to this point is L cos theta. Okay, so this small distance h can be written as, therefore h is equal to what I can write? Total length L into projection of L on this one. That is nothing but L cos theta. L minus L cos theta. That is equal to what you will be getting? L into 1 minus cos theta. This you can substitute here. Therefore, gravitational potential energy Ug is equal to mgL into 1 minus cos theta. Okay, this is the gravitational potential energy of the bob with respect to line number 1. And work done by gravity is equal to what I can write straight away? Negative of change in potential energy. Initial potential energy is anyhow 0, because of which you will be getting how much? Minus mgL into 1 minus cos theta. Okay, now by taking the second reference line, that is this as the reference, I am calculating the potential energy. Okay, so with respect to this, the bob is at a depth, let me call it as y. This distance I should calculate here. Okay, so this distance is nothing but projection of L on this one. Distance is nothing but this one. That is how much? Y only. Y is equal to, already I calculated how much it is? L cos theta. Here y is equal to L cos theta. As the bob is lying below the reference line, therefore potential energy Ug is equal to what I can write? Minus mg into y, which is nothing but minus mg into what is y? L cos theta. L cos theta. Minus mg L cos theta is the potential energy. Have a look at it. When you consider this horizontal line as the reference, this is the value of potential energy. When you consider this as the reference line, this is the value of one. So the value of potential energy depends on the reference line. But if you calculate change in the potential energy, delta U, if you calculate the change in potential energy, which is nothing but UF minus UI, okay, the value should be same. Let me check it. So with respect to this reference line, when the bob is at mean position, what is the potential energy? That I am calling it as UI is equal to the distance of bob from this reference level is L only. So minus mgl. And UF, when it is tilted through angle theta, how much we got? This one. Therefore, if you calculate the delta U, which is nothing but UF is how much? Minus mgl cos theta minus UI is how much? Minus mg. So minus into minus plus, if you take L as common, mgl as common, what you will be getting? 1 minus cos theta you will be getting. So if you look at this, if you calculate delta U by considering this as a reference line and delta U by considering this as a reference line, in both the cases are not only these two, any lines that you consider, the change in the potential energy, gravitational potential energy is going to be same. So through this what we can conclude, potential energy you can't define absolutely. You have to consider one reference, and with respect to that reference only we can talk about the potential energy. But because of which it may change depending on the reference level that we consider. Whereas change in the potential energy is always same, whatever it may be the reference that you consider. Okay, that is one of the important observations regarding the gravitational potential energy, or not only gravity, any potential energy. And work done by gravity, if you calculate, which is negative of change in potential energy, which is nothing but minus mgl into 1 minus cos theta. This is how we calculated potential energy and change in potential energy in different cases.